All right, so in 11.5, we are looking at matrices. Now, for matrices, it seems like such a change of pace for us because we were just solving systems of equations. So what do matrices have to do with systems of equations? Well, we're going to see that in a few minutes, but first, we have to understand what a matrix is to be able to work with them. All right, so a matrix is basically just a rectangular array of numbers. It kind of reminds me of like a spreadsheet. It's just a way to organize data, and we organize it in rows and columns. Now, some people get rows and columns confused. So think about for just a second, if you go to a concert and you're sitting in row 5, those rows go across, right? But if you think about some of the beautiful architecture downtown, you have the columns in the front of the building that go up and down that support the structure. So if you kind of visualize those two things in your mind, it might help you remember which are your rows and which are your columns. Okay, so we're going to give the order of the matrix, and it's going to be the number of its rows times the number of its columns. So if we look at this matrix, how many rows does it have? 3. And how many columns does it have? 4. So its order would be a 3 by 4. Now, every number in that matrix is called an entry, and we can represent each of those entries with a subscript. So the first number in the subscript tells you what row it's in, and the second number tells you what column it's in. All right, so we're looking for the number or the entry that is in row number 2 and column number 3. So what's in row 2 and column 3? 7, exactly. All right. So we can add, subtract, matrix multiply, and scalar multiply with our matrices. So those are the things the operations that we want to look at. To begin with, 2 matrices are going to be equal to each other if they have the same order and all of the same elements or all of the same entries. So when they tell me that these first 2 matrices are equal to each other, then I automatically know that what's in the first row, first column in the first matrix has to be the same thing as what's in the first row, first column of the second matrix. So I know that X is equal to 3. So first row, first column equals first row, first column. So X is equal to 3. Then you can see 2 is equal to 2. And 3y minus 1 would have to be equal to what? 8. And then 5 is equal to 5. So if 3y minus 1 is equal to 8, then we would be able to solve that to figure out what y would be as well. Now, most of the time when they give you a matrix, they're going to use a capital letter for the matrix, and they're going to use like brackets around it for to designate that it's a matrix. So when I see something like what we've got down here in example 3, where we've got the capital A and we've got the brackets on it, we'll automatically know that that's a matrix. Okay? All right, now, matrices can only be added or subtracted if they have the exact same order. So if you have different orders, then we say that that sum is undefined. So it has to be exactly the same. It has to be a 3 by 4 and a 3 by 4, a 1 by 6 and a 1 by 6. They have to be identical. All right. So here they ask me to add A plus B. All right. So if I'm going to add A plus B, I'm going to take what's in the first row, first column, plus what's in the first row, first column, and I'm going to put it in the first row, first column. So I'm going to say 2 plus 2 is equal to 4. All right. Then I'm going to do the same thing, first row, second column. I'm going to take what's in the first row, second column, 2, plus first row, second column, 0. And that's going to give me my answer that goes in the first row, second column of 2. And we could keep right on going. So we could say, 4 plus 0 is equal to 4, and that finishes off that first row. And then for the next one, negative 3 plus 1 is negative 2. 0 plus negative 4 is negative 4. Negative 1 plus 3 is 2. You get the idea. Now, you do not have to show any work at all for this. I understand you can do that in your head. The only reason I have any work on here is it doesn't do you a whole lot of good for me to give you the question and then the answer and, not anything in between. If we were going to subtract, we would do the exact same thing except for we would subtract. So we would say like 2 minus 2 is equal to 0 for the first row, first column. And 2 minus 0 is equal to 2. And 4 minus 0 is equal to 4. And that would be our first row. So adding and subtracting work the exact same way. All right, then the next thing that they give us is scalar multiplication. All right, scalar multiplication is literally when I multiply a matrix by a scale factor. So like in this case, I'm tripling it. I'm multiplying it by 3. So I'm literally going to go through and multiply each of those numbers by 3. So I'm just going to say 3 times 2 is 6. 3 times 2 is 6. 3 times 4 is 12. 3 times negative 3 is negative 9. 3 times 0 is 3. 3 times negative 1 is negative 3. You get the idea. All right. So that's how we're getting this new matrix over here. All right. So again, that's scalar multiplication. So then they'll start putting those things in combination. Like they might have us do scalar multiplication and addition or subtraction. All right. I got to follow order of operations there. So I would need to do my multiplication first. I would do the 3 times A. Now that's the one that we just did, right? That was that answer we just got. So let's go ahead and put that down here. That's 3A. And then we're going to subtract matrix B that they gave us up here at the top. All right. And so again, to subtract, we're just going to take what's in the first row, first column, minus what's in the first row, first column, put it in the first row, first column. So we're just going to say 6 minus 2 is 4. 6 minus 0 is 6. 12 minus 0 is 12. Negative 9 minus 1 is negative 10, and so on. Now, let me just make a suggestion to you. If you have a problem, something like this, so they give me something like 3x plus a is equal to b. Rather than going ahead and putting in matrix A and matrix B and having like this great big thing with all these numbers in it, and then in the next step you got to rewrite them both again, and then in the next step you got to rewrite them both again, it's a good idea to just leave the letters in there for the matrix and then go ahead and solve that like you normally would. And once you figure out that x is equal to 1/3 times b minus a, then you can go back and do the same kind of thing that we were doing down here with 3a minus b. Okay, so just a suggestion might make it a little bit easier. All right, if there's anything challenging about matrices, it is multiplying them because they do not work the way we think they should. We think that we should be able to say 2 times 7 is equal to 14. That's not 14 right there. So I don't do multiplication the same way I do addition and subtraction. I can't take what's in the first row, first column times what's in the first row, first column and put it in the first row, first column. I got to do it differently. So here's how I multiply matrices. First off, their order is really important, okay? The order is how you tell whether you can multiply and what your answer is going to look like. All right, so you'll notice that when you're multiplying matrices, the inside numbers in the order have to be the same in order for you to be able to multiply. All right, so if you look at this first example, we've got a 2 by 2 and a 2 by 2. The inside numbers were the same. Look at this next one. The next one, I have a 1 by 2 and I have a 2 by 3. Could you add those? What has to be true for you to add? They have to be identical, right? Exact same order. So I couldn't add or subtract these, but I can multiply them because their inside numbers are the same, okay? So what if their inside numbers are not the same? Then it can't be done. So if you come down here and you look at this last one, For our inside numbers, we have 2 and 1. If it's not the same, it can't be done. And so we just say that it's undefined. No solution, impossible, can't be done, whatever WebAssign tells you that it wants you to put, does not exist, whatever. But we'll use undefined. All right, so let's go back and look at how I do multiply matrices if I don't do it that other way. Something else that's important is that the outside numbers in your order tell you the order of your answer. So if I look at this first one, my outside numbers are a 2 by 2. So that tells me that my answer is going to be a 2 by 2. So I'm going to go ahead and come over here, and I'm going to give myself 4 blanks for a 2 by 2. If I want to know what goes in the first row, first column, I multiply the first row times the first column. If I want to know what goes in the first row, first column, I multiply the first row times the first column. So I'm going to take 2 times 7 plus 3 times 8. So 2 times 7 plus 3 times 8 is where that 38 is coming from. All right, if I want to know what goes in the first row, second column, I'm going to multiply first row by second column. So I'm going to multiply my first row 2, 5 times my first row 2, 3 times my second column 1, 6. So 2, 3 times 1, 6. So 2 times 1, 3 times 6 is where I'm getting that 20. Okay, what is 67 in terms of row and columns? What's its location in the matrix? What row is it in? Second row. What column? First. So if it's in the second row, first column, that tells me what to multiply. I multiply second row times first column. All right? So I'm going to come over here and I'm going to multiply second row 5, 4 times first column 7, 8. So we would do 5 times 7, 4 times 8, add those together, and that's where we get the 67. All right, how about 29? Where is it in the matrix? What row, what column? Second row, second column. So what am I going to multiply? Second row times second column. Yes. So let's take that second row, 5, 4, and multiply it by that second column, 1, 6. So we would do 5 times 1 and 4 times 6. Add those together to get the 29. All right, look at another one of those. The first thing that I want to do is I want to check to make sure that my inside numbers are the same, because I can't multiply if they're not, right? But here's the next thing I want to do. I want to look at my outside numbers to see the order of my answer. I get 1 and 3. I have to know the order of my answer because that's what tells me what to go multiply, right? So I'm going to go ahead down here and I'm going to draw out for myself a 1 by 3. I'm going to give myself a row with 3 answer blanks in it. So then if I want to find what goes in the first row, first column, what do I multiply? First row times first column. So I'm going to take my first row, 6, 8, and I'm going to multiply it by my first column, 1, 4. So I would do 6 times 1, 8 times 4, and add those together to get my 38. All right. So then I want to find first row, second column. So what am I going to multiply? First row times second column. So I'm going to take 6, 8 times 5, 6. So I'm going to do 6 times 5 and 8 times 6 to get that 78. And then for my last one, what's the position of this last one in terms of rows and columns?
First row, third column.
First row, third column. So we're going to multiply first row times third column. So 6 times 3, 8 times 2 will give us that 34 when we add those together. And as we already mentioned for this last one down here, because the inside numbers were not the same, then we can't multiply. Okay? So as you can see, the order of matrices is really, really important. Like, it determines whether you can add and subtract and multiply and all of that kind of stuff. Order in our lives is really important too. I mean, especially as we're talking about going into final exams and finishing out the semester, like, we need structure and order in our schoolwork, in our athletics, and our extracurriculars, and in our walk with Christ. I think it's easy for us to, we get our calendar out and we put all of our tests on there and when we're going to study and don't forget this homework, and we map it all out. We have a plan for academic success. You set goals for yourself that you're going to work out 5 days a week, or, each day you're going to bench more than you did the day before. You have specific goals. Do the same thing for your spiritual life. Set aside, I'm going to read my Bible and pray, or read a devotional book, or listen to a podcast or something that would be encouraging. I'm going to do that however many days a week for however much time. Set a goal for that, just like you would anything else. 1 Corinthians 14 tells us that everything needs to be done decently and in order, because we are structured that way. That's what helps us tick. That's how God made us, because God is a God of order as well. All right, couple last things about our matrices. When we talk about properties of matrices, most matrices have the same properties as normal multiplication. But there's one thing that's different, and that is that A times B is not equal to B times A when we're talking about matrices. All right? If we look at this second example over here that we had a 1 by 2 and a 2 by 3, right? Okay, so if I have a 1 by 2 and a 2 by 3, let's reverse that order. So let's say instead that we had done the 2 by 3 first and the 1 by 2 second. Your inside numbers are 3 and 1. They're not the same. You can't even multiply that, right? So we were able to multiply it up here. When we did this particular order, we could say A times B. But if you reverse that order and you had the 2 by 3 first times the 1 by 2 second, it can't even be done. So that's an easy way for us to see that A times B is not necessarily the same thing as B times A. All right? Then something that we're going to utilize a great deal moving forward is the identity matrix of multiplication. All right? What's the identity of multiplication? Forget matrices for a second. What's the identity of multiplication? Been a long time since we learned those, guys. Identity of multiplication is 1, because you multiply any number times 1 and you get what you started with, right? That is exactly what these matrices do. If you multiply any 2 by 2 matrix times the 2 by 2 identity, you just get that matrix you started with. If you multiply a 3 by 3 times the identity, you get what you started with. So we could keep going with that 4 by 4, 5 by 5, 10 by 10 if we wanted to. Here's what the identity matrix is. In this diagonal that goes from first row, first column to last row, last column, we call that the main diagonal. That will be all 1s. Everything else will be 0s. So if I was drawing a 10 by 10, I would put 1s in the main diagonal that went from first row, first column to 10th row, 10th column, and I'd put 0s everywhere else. Okay? So that's our identity matrix. All right, so I want you to understand why in the world we're doing these matrices when we've been talking about systems. And so I want to get just a little bit into section 11.6, just so you can see how this fits together. All right, so remember that we started off talking about the order of matrices, that like this one was a 3 by 4. We also talked about how you could label each individual number in the matrix as an entry. All right, so let's say that we have this system of equations right here. I could take out all the letters and just organize the numbers into a matrix. So if you'll notice, if I just take the numbers, I'm going to have for the first equation up here, that would be 1, -4, 3, 5. And look at the first row of your matrix, 1, -4, 3, 5. All right, same thing with the second row, -1, 3, -1, -3. And then same thing with the third row, 2, there's no y value, so that's 0y. So that would be 2, 0, -4, 6. So this is called an augmented matrix. And the augmented matrix is just your system without the letters in it, so that you can just focus on the numbers and getting them to getting your solution. Now, what would the order of our augmented matrix be? Rows and columns. What's my order? 3 by 4. Yes, so 3 rows and 4 columns. Now, if we took off just this last column, all right, because that was what was on the other side of the equal sign. You'll notice the little dotted line right here that kind of designates where the equal sign would go. So if I take off this last column and all I have left is this 3 by 3, what are all of those numbers? What do you call a number in front of a variable? Coefficient, right. So we call that the coefficient matrix. So if that last column is gone, what was on the other side of the equal sign, and all I'm left with is what was on the one side of the equal sign, then we call that our coefficient matrix. Now, that coefficient matrix, what's the order of that? 3 by 3. So a 3 by 3 or a 4 by 4 or a 5 by 5 or a 2 by 2, when the number of rows and columns are the same, we call that a square matrix. So when the number of rows and columns are the same, it's a square matrix. And then also remember, we talked just a moment ago about your main diagonal. Your main diagonal goes from first row, first column to last row, last column. So 1, 3, -4 would be in my main diagonal. So that's just some terminology that they will use moving forward with our matrices. All right, so look at example number 2. For example number 2, we want to write an augmented matrix for this system. Now, let me suggest to you that you rewrite that system first. Because if you'll notice, you've got X, Y, and Z in here. And so there's something missing in each one of the equations that I want to fill in. So for instance, on the first one, I've got 1x plus 3y, and I had no z. So I'm going to fill in a 0z for that one is equal to 9. All right, how about your second equation? What do you need to fill in? 0x, yeah. So I would have 0x minus 1y plus 4z is equal to -2. All right, now my last equation, I got all kinds of stuff going on because order is important. It does need to go X, Y, Z. So I'm missing a Y term and this is not in the correct order. So how would I want to write my third equation? How many X's? 1x. How many Y's? 0y. And then we had the minus 5z. Okay, so now that I've rewritten my system, then I can write my augmented matrix. All right, so what's going to be in the first row of my augmented matrix? Perfect. 1, 3, 0, 9. How about my second row of my augmented matrix?
0, 4.
And then our last row would be 1, 0, negative 5, 0. So we should be able to go either way with this. They should be able to give me the augmented matrix and me come up with a system. This is 1x plus 3y plus no z is equal to 9. Or they should be able to do as they did here, give me the system and me find the augmented matrix for it. Now, you might remember back when we were solving systems of 3 equations with 3 unknowns. We did it the Algebra 2 way. We took equations 1 and 2 and combined them and eliminated a variable. And then we took equation 2 and 3 and eliminated the same variable. And that gave us 2 new equations, 4 and 5. And then we solved that for a system. And then we back substituted all the way through. And it took like half a sheet of paper to do one problem, right? And they had told us at that point that another way of solving was to use Gaussian elimination. Gaussian elimination named after Carl Friedrich Gauss, who kind of discovered the idea. And so for Gaussian elimination, I'm going to use elementary row operations to solve a system. What is an elementary row operation? Okay, there are 3 things that you can do with matrices that are row operations. The first one is you can switch any 2 rows in a matrix. Now, not columns, but rows. You can switch any 2 rows. Well, how can I do that? Like, how does that not change anything? Well, come over here and think about the system that's associated with that. Could you switch the second and third equation in that system? That wouldn't change anything, right? Doesn't make a difference if I call this number 2 and this number 3, or this number 2 and this number 3. It's the same system, right? So we can see why we would be able to switch 2 rows in the matrix as well. All right, the next thing that we can do is we can multiply a row by a constant. Okay, how can I just throw 2 into one row of the matrix and not mess it up? Well, come over and think about the system again. Over here on your system, can you multiply both sides of an equation by 2 in that system and not mess it up? Absolutely. We did that for elimination all the time, right? Like we would go through and we would multiply this by a positive 2, so we'd have a negative 2x and a positive 2x that would eliminate, right? So if I can do it to the equation, I can do it to the matrix. And then the third thing that I can do is I can multiply a row by something and add it to another row. So again, it's that idea over here where we took 2 times negative x and got a negative 2x so that we could add it to this other equation so that we could get them to drop out, right? So the same idea over here with my matrices, I can multiply a row by something and add it to another row. All right, so let's practice each of those row operations. I don't really think we need to practice switching 2 rows. That's pretty obvious. All right, but look at example 3C. They ask us to do negative 2 times row 1. All right, so let's take row 1, 1, 2, negative 4, 3, and let's just multiply it by negative 2. So negative 2 times 1, negative 2, negative 2 times 2, negative 4, I think we all know this, negative 2 times negative 4, positive 8, and then negative 2 times 3, negative 6. All right, so that's how we multiply a row by a constant. All right, then the next thing that they ask us to do is they ask us to multiply a row by a constant and then add it to another row. Multiply a row by a constant and then add it to another row. So you can see over here, we're going to copy row 1 and 2 exactly as they are, but we're going to change row 3 because we're going to multiply negative 2 times row 1 and add that to row 3. It's going to change row 3. So we already did negative 2 times row 1 right up here. So we'll just bring that down and we'll add it to row number 3. So row number 3 was 2, 1, 5, negative 2. So again, here's our negative 2 times row 1. Here's our row 3. We're just going to add those together. All right, so negative 2 and 2, 0, negative 4 and 1, negative 3, 8 and 5, 13, 6, negative 6 and negative 2. So those are our 3 elementary row operations. The last thing we want to talk about today is row echelon form and reduced row echelon form, because we're giving ourselves all the tools and all the terminology that we're going to need to, in our next lesson, be able to solve a system using our matrices. All right? So row echelon form is when you have a matrix where the first non-zero number in every row is a 1. So first non-zero number is a 1, first non-zero number is a 1, first non-zero number is a 1. We call that a leading 1 because it's a 1 that's leading the numbers, right? The leading 1 in a higher row has to be further to the left than a leading 1 in a lower row. So you can see in the first row, the leading 1's further to the left than the second row, and in the second row, it's further to the left than the third row. So that is row echelon form. Now, look at this for just a second. What is the system that goes with this augmented matrix? It would be 1x plus 2y minus z is equal to 4. No x plus 1y plus no z is equal to 3. No x, no y, 1z is equal to negative 2. That's that little stair-step system that we solved a couple of sections back. It was so much easier to solve when it looked like that. So we're going to use these elementary row operations to transform whatever matrix they give us into row echelon form, and then it'll make that system so much easier to solve. All right? Look at this second one right here. Is this in row echelon form? All right. Is the first non-zero number in every row a 1? Yes. And is the leading 1 in the higher row further to the left than the lower row? Yeah. So it doesn't have to be just one stair step over like it was in that first one. As long as the leading 1 in the higher row is further to the left than the leading 1 in the lower row, then it's fine. All right. And then the last matrix over here introduces a row of zeros. So that's kind of strange. If you have a row of zeros in row echelon form, it has to be at the very bottom. So this row of zeros is at the very bottom. Is everything else true about this, that it's in row echelon form? Yeah, because every non-zero, the first non-zero number is a 1, and each leading 1 is further to the left than the right, than the one below it, and then all the zeros are in the bottom row. All right, look at this augmented matrix, this second one right here. And let's think about the system that would be associated with that. Look at your very last row and tell me what the solution to that system would be. So in your last row, you're going to get 0x plus 0y plus 0z is equal to 1. You're going to get 0 equals 1. What's the solution to that system? No solution, right? So that's what no solution looks like in matrices, all right? Look at this last one over here that we were just talking about. And again, look at your last row. What would the solution to that system be? I'm going to have 0x plus 0y plus 0z is equal to 0. So I'm going to have 0 equals 0. What is that? Infinitely many solutions. So that's what it would look like. We have an example of one solution, no solution, and infinitely many solutions. Now, that's row echelon form. If I'm willing to do a few more elementary row operations, I can change this into something called reduced row echelon form. So if I go back to this very first matrix we worked with over here, if I was willing to do a few more row operations to transform this -1 and 4 into zeros, then it would give me reduced row echelon form that you see right here. Well, what's the big deal about reduced row echelon form? The only difference is above and below every leading one, you have all zeros. Above and below every leading one, you have all zeros. So that's why these had to change to zeros. Why is that helpful? What is the system associated with this augmented matrix? What's your first one? What's your first equation in this augmented matrix from row 1? X equals 4. That's 1x plus no y plus no z equals 4, right? That's x equals 4. What's the next one? Y equals 3. What's the last one? Z equals -2. Y'all, that's my answer right there, right? X, Y, Z. So that's how we're going to use matrices to solve systems. We're going to take whatever matrix they give us, and we're going to use elementary row operations to transform it into either row echelon form, where we could back substitute, or reduced row echelon form. All right. So now we have all the tools that we're going to need to do that process in our next lesson.